Tonight, we're going to explore one of the strangest things happening in our solar system. Saturn's rings are disappearing. There are billions of icy fragments circling the planet. Some are smaller than grains of dust. Some are as large as boulders. Together, they form a ring system that stretches hundreds of thousands of kilometers around Saturn, wide enough to make the planet one of the most recognizable worlds in the night sky. Given those numbers, something so enormous should feel permanent. Yet instead, we see a ring system that is slowly falling apart. Tiny pieces of Saturn's rings are being pulled down into the planet's upper atmosphere. Scientists call this process ring rain. It is a strange flow of icy material, guided by Saturn's gravity and magnetic field, slowly draining the rings from above. And by the end of tonight, you're going to understand why that might mean Saturn is wearing a crown that was never meant to last. Because when we look at Saturn, we usually see something timeless. A pale golden planet surrounded by wide, bright rings. It looks ancient, balanced, almost frozen in place. But Saturn is not frozen in place. Its rings are active. They are shifting, colliding, spreading, darkening, and slowly losing material into the planet below. What looks like a perfect cosmic ornament is really a moving system of ice, dust, gravity, magnetism, and time. And that is where the contradiction begins. Saturn itself is more than 4 billion years old. It formed in the early solar system when the planets were still growing out of a wide disk of gas and dust around the young sun. It has survived asteroid impacts, shifting moons, violent storms, and billions of years of orbiting in the cold outer solar system. But the rings may be far younger than the planet. Some interpretations of Cassini spacecraft data suggest the bright rings could be only a few 100 million years old. That is still ancient compared with human history. But besides Saturn's full lifetime, it is surprisingly recent. If that is true, then the Saturn we know may be a temporary version of Saturn. For most of its existence, the planet may have looked very different. Still huge, still cold, still wrapped in clouds and storms, still surrounded by moons, but without the wide, shining rings that now define it in our mind. And in the far future, it may look different again. The rings may keep thinning. More icy grains may fall into Saturn as ring rain. More material may be lost, scattered, or darkened. And after enough time passes, the broad, bright rings that make Saturn so famous could fade into something much smaller, dimmer, and harder to see. That is the unsettling part. We may be living during a rare window in Saturn's life. A window when the rings are still bright enough, wide enough, and clean enough to dominate the planet's appearance. A future observer may look at Saturn and see only a gas giant. Beautiful, perhaps. Enormous, certainly. But missing the thing that made generations of humans stop and stare. So tonight, this is the journey we are going to follow. How Saturn's rings can seem to vanish from Earth. How something so wide can also be incredibly thin. How icy particles become charged and fall into Saturn as invisible rain. How Cassini changed what scientists thought they knew about the rings. And why the most iconic structure in the solar system may be one of its most temporary. Because the deeper we look at Saturn, the less it feels like a finished planet. It feels like a planet caught in the middle of a chapter that began with ice and gravity, a chapter that may have started with destruction, and a chapter that is slowly ending one falling particle at a time. Before we go deeper, we need to understand why Saturn's rings feel so permanent in the first place. Because humans have only been watching them for a tiny fraction of their real story. If you enjoy calm journeys through the stranger parts of space, take a moment to like the video and subscribe. It helps this channel reach more curious viewers who love exploring the universe slowly, quietly, and deeply. Now, let's continue. Saturn feels permanent because every human who has ever looked at it through a telescope has seen the same basic wonder. A pale golden planet, a wide flat ring system, a shape so unusual that it seems almost designed. But our history with Saturn is extremely short. Saturn itself formed about 4.5 billion years ago, during the early formation of the solar system, when the Sun was still surrounded by a rotating disk of gas, dust, ice, and rock. Out of that disk came the planets, moons, asteroids, comets, and the first raw architecture of the solar system we live in now. Saturn has been orbiting the Sun for almost as long as Earth has existed. Each Saturn year lasts about 29.5 Earth years. That means, since the planet formed, Saturn has completed roughly 150 million trips around the Sun. Every orbit carried it through the cold outer solar system, about 1.4 billion kilometers from the Sun on average, nearly 10 times farther away than Earth. And yet humans have only seen its rings for a few hundred years. For almost all of human history, Saturn was simply a wandering point of light. Ancient skywatchers could track it moving slowly against the background stars, but they had no way to know what it really was. To the naked eye, Saturn gives away almost nothing. It looks calm, steady, and distant. Then, in 1610, Galileo Galilei pointed one of his early telescopes at Saturn. The telescope was crude by modern standards. Its lenses were small. The image was blurry. The magnification was limited. But Galileo saw something strange. Saturn did not look like a clean round disk. It seemed to have two smaller shapes attached to its sides, almost like handles or ears. He could see that something was there. He could not clearly see a ring. Over the next few years, Saturn's appearance changed as Earth's viewing angle shifted. At times, the side shapes seemed to shrink or vanish. Galileo was puzzled. The planet looked as if it could change shape, as if the strange objects beside it could appear and disappear. The real explanation would come later. In 1655, the Dutch astronomer Christian Huygens used a better telescope and recognized that Saturn was surrounded by a thin, flat ring that was separate from the planet itself. This was one of the great discoveries of early telescopic astronomy. Saturn was not a simple wandering star. It was a world with a structure around it, a structure unlike anything humans had ever seen. A few decades after that, Giovanni Domenico Cassini observed a dark gap in the rings, now called the Cassini division. That gap helped show that the rings were not one solid band, but a more complex system with separations and structure. Piece by piece, Saturn became the planet of rings in the human imagination. But that imagination is based on a tiny slice of time. From Galileo's first confusing view in 1610 to now is just over 400 years. Compared with Saturn's age, that is almost nothing. If Saturn's 4.5 billion year history were compressed into a single 24-hour day, the entire era of telescopic observation would last less than a single fraction of a second. That is why the rings feel eternal. We arrived late, looked up during one brief moment, and assumed the scene had always been this way. But a planet can change slowly enough that generations miss it. A ring system can lose material grain by grain. A structure can seem frozen because the clock it follows is far larger than a human life. And Saturn's rings are built on exactly that kind of clock. To understand how something can appear so permanent while quietly changing, we have to begin with the first way the rings disappear, the way they can vanish almost completely even while they are still there. The first disappearance is the one humans can watch from Earth. Saturn's rings have not always looked wide and open in our telescopes. Sometimes they narrow into a thin, bright line. Sometimes, through smaller telescopes, they seem to almost vanish. This happens because Saturn is tilted. Earth is tilted by about 23.5 degrees, which gives us our seasons. Saturn is tilted by about 26.7 degrees, a similar kind of lean, though Saturn takes much longer to move around the Sun. One Saturn year lasts about 29.5 Earth years, so its seasons are long and slow. Each season on Saturn lasts more than 7 Earth years. As Saturn follows its orbit, Earth sees the rings from changing angles. For several years, the northern face of the rings is tilted toward us. The rings look open, bright, and wide. Then the angle slowly flattens. The rings turn more and more edge-on. Eventually, Earth lines up almost exactly with the ring plane, the flat sheet where the rings orbit. When that happens, the rings become extremely hard to see. They have not disappeared from Saturn. They have turned sideways from our point of view. It is similar to holding a sheet of paper flat in front of your face, then slowly rotating it until you see only the thin edge. The paper is still there. Its width is still there. Its surface has simply stopped facing you. Saturn's rings do this on a planetary scale. The main rings stretch across hundreds of thousands of kilometers, yet their vertical thickness is tiny compared with their width. In many places, the rings are only around 10 meters thick. That is about the height of a 3-story building. So when Earth sees them edge on, we are looking across an enormous icy structure from its thinnest side. That is why the effect is so strange. A ring system wide enough to dominate one of the largest planets in the solar system can shrink into something almost invisible, simply because the viewing angle changes. This edge-on event happens roughly every 13 to 15 years. Saturn's full orbit takes nearly 30 years, and during that orbit, we pass through the ring plane about twice. Each time, the rings seem to close, vanish, then open again as Saturn continues around the Sun. Galileo saw this confusion early. In 1610, he noticed Saturn had strange side features. Then, around 1612, those features seemed to disappear. He did not yet know he was watching the ring system turn edge-on. To him, Saturn looked as though it had changed shape, almost as if the planet had swallowed the objects beside it. Centuries later, we understand the geometry. The 2025 ring plane crossing was part of this same cycle. Saturn's rings became nearly edge-on from Earth, creating a temporary visual disappearance. With large telescopes, the rings could still be studied. With casual viewing, they became far less dramatic, reduced from Saturn's defining feature into a narrow line of light. Then, slowly, they begin to open again. The disappearance reverses. The ring system returns to view. For someone watching across a decade, Saturn seems to breathe. The rings widen, flatten, vanish, and widen again. It is a slow celestial rhythm caused by tilt, orbit, and perspective. But this first disappearance is only geometry. It shows how fragile the rings can look when seen from the wrong angle. It reminds us that Saturn's most famous feature is not a solid crown attached to the planet. It is a thin, flat, delicate structure seen from far away. And that visual vanishing points towards something deeper, because there is another kind of disappearance happening around Saturn, one that does not reverse when the angle changes, one that is not caused by perspective. The rings are not only turning sideways in our sky. Some of their material is actually leaving the ring system. It is falling out of orbit, moving down along magnetic pathways, and entering Saturn itself. Before we can understand how Saturn is losing its rings for real, we need to understand how something so enormous can also be so thin. Saturn's rings look massive because they stretch so far from the planet. From one side of the main ring system to the other, they span a region wider than several Earths placed side by side. The broad, visible rings begin tens of thousands of kilometers above Saturn's cloud tops and extend outward for hundreds of thousands of kilometers. From a distance, they look like a solid flat disk wrapped around the planet. But their size is misleading. The rings are wide, but they are almost impossibly thin. In many places, the main rings are only about 30 feet thick, or roughly 10 meters. That is about the height of a 3-story building. Some parts may be thicker, some thinner, especially where particles clump, collide, or form waves. But compared with the full width of the rings, their vertical thickness is tiny. This is what makes Saturn's ring system so strange to picture. Imagine a structure wide enough to cross the distance from Earth to the Moon, but with the thickness of a small building. Or imagine a sheet of paper stretched across a city, so thin that from the side it almost disappears. Saturn's rings are like that, except the sheet is made of ice, dust, and countless orbiting fragments. That is why the rings can vanish so easily when they turn edge-on from Earth. We are looking across the thinnest part of an enormous structure. The rings are sometimes described as flat, but even that word can make them feel more solid than they really are. They are not a smooth floor. They are not a single plate of ice. They are a thin orbital swarm, with trillions of separate particles circling Saturn at different distances and speeds. The inner parts of the rings orbit faster than the outer parts. That happens because of gravity. Close to Saturn, particles feel a stronger pull from the planet, so they move more quickly to stay in orbit. Farther out, the pull is weaker, so particles move more slowly. This means the rings are constantly sliding past themselves, with different lanes moving at different speeds. Even the names of the rings show how complex they are. The brightest main rings are called the A ring, B ring, and C ring. The B ring is the brightest and densest. The A ring sits farther out. The C ring lies closer to Saturn and appears fainter, almost transparent in some observations. Between the A and B rings is the Cassini division, a dark gap about 4,800 kilometers wide, first observed in the 1600s by Giovanni Domenico Cassini. From Earth, those features blend into a graceful shape. Up close, they become a landscape of lanes, gaps, waves, ripples, edges, and shadows. Saturn's moons help carve some of those structures. Tiny moons can tug on ring particles, clearing gaps or sharpening edges. Larger moons can create repeated gravitational pulls that move through the rings like waves through water. The result is a system that looks smooth from far away, but is busy everywhere inside it. And because the rings are so thin, small changes matter. A slight tilt changes how much light they reflect toward Earth. A small moon can sculpt a gap. A stream of charged particles can remove material. A collision between icy fragments can create dust, spread debris, or change the path of nearby grains. The rings look like a monument, but physically they are delicate. Their beauty comes from their thinness, their brightness, and their enormous spread around Saturn. The same features that make them stunning also make them vulnerable. A structure this thin can be shaped by forces that would be invisible from Earth. Gravity can bend it. Moons can stir it. Magnetic fields can pull at charged grains. Impacts from tiny meteoroids can darken, chip, or scatter its ice. Once the rings stop feeling like a solid crown and start feeling like a thin sheet of moving material, their disappearance becomes easier to understand. Saturn is not losing one object. It is losing pieces. And those pieces are not all the same size. Some are as fine as smoke. Some are as large as rocks. Some are hidden in dense bands. Some drift through faint outer lanes. To understand how Saturn can lose its rings, we need to look closer at what the rings actually are. From far away, Saturn's rings look smooth. They seem like wide bands of light wrapped neatly around the planet, almost like a single object. But the rings are really a swarm. They are made of countless separate pieces, each one moving around Saturn under the pull of gravity. Most of this material is water ice. That is one reason the rings look so bright. Ice reflects sunlight well, especially when it is relatively clean. Mixed into that ice are smaller amounts of darker dust, rocky material, and chemical compounds that have been delivered by tiny meteoroids over time. So the rings are not empty light. They are physical. A frozen, dusty, orbiting system. Some particles are smaller than grains of sand. Some are like snowballs. Some are the size of rocks, furniture, cars, or houses. A few larger clumps and moonlet-sized objects also move within or near the rings, helping disturb and shape the material around them. If you could float safely near the rings, they would probably look very different from the smooth images we see from telescopes. Nearby, you might see dark space between drifting ice fragments. You might see flat slabs, rounded chunks, shattered pieces, and dusty grains sparkling in weak sunlight. Some would tumble slowly. Some would collide gently. Some would break apart and add more dust to the swarm. Each piece is following its own orbit. That is one of the most important things to understand. The rings are not spinning like a solid record. A solid record turns as one piece, with the inner and outer parts rotating together. Saturn's rings behave differently. The particles closer to Saturn move faster because they feel a stronger gravitational pull from the planet. Near the inner main rings, particles can travel at more than 20 kilometers per second. Farther out, they move more slowly, closer to 16 or 17 kilometers per second. That means different lanes of ring material are constantly sliding past one another. This is called differential rotation. It simply means that different distances from Saturn orbit at different speeds. The result is a ring system that is always moving, always grinding, always adjusting. Particles bump into each other. Dust spreads. Clumps form and break. Tiny moons tug on the nearby ice. Gravity creates waves that ripple through the rings like patterns in a pond. And because each particle is separate, each particle can have a different fate. One grain might stay in orbit for a very long time. Another might be struck by a micrometeoroid, a tiny piece of space debris moving fast enough to chip or vaporize ice. Another might become electrically charged by sunlight or plasma near Saturn. Another might drift inward. Another might be pulled into a slightly different path by one of Saturn's moons. The ring system survives as a whole, but the individual pieces are constantly being affected. That is why the word swarm matters. A swarm can be shaped. A swarm can be stirred. A swarm can be slowly drained. The rings are held in place by motion. Every icy fragment is falling towards Saturn, but also moving sideways fast enough to keep missing the planet. That is what orbit is. It is a continuous fall around a world instead of straight down into it. But this balance is delicate. A particle only stays in the ring system if its motion remains just right. Change its speed, its charge, or its direction, and it can start to migrate. It can collide. It can drift into a new lane. It can become part of a faint, dusty band. Or, under the right conditions, it can leave the rings entirely. This makes Saturn's rings feel less like a crown and more like weather. A vast frozen weather system made of ice and gravity. There are patterns, but there is also constant motion. There is structure, but there is also loss. There is beauty, but it comes from trillions of small objects doing separate things around one enormous planet. And once the rings become a swarm, their disappearance becomes easier to imagine. Saturn does not have to destroy the rings all at once. It only has to disturb the pieces, grain by grain, fragment by fragment, orbit by orbit. And the forces doing that are already built into the Saturn system itself. The rings survive because every particle is caught in a balance. Saturn's gravity pulls inward. The particle's sideways motion carries it around the planet. Together, those two motions create an orbit. If an icy grain had no sideways speed, it would fall straight down into Saturn. If it moved too fast, it could drift away into a wider path. But at the right speed, it keeps falling around the planet, circling again and again through the same broad ring plane. That is what makes the rings possible. Saturn is enormous. It is about 95 times more massive than Earth, with a diameter of about 120,500 kilometers at its equator. Its gravity dominates everything nearby. from the smallest dust grains to large moons like Titan, which is bigger than Mercury. Every ring particle feels that pull. The particles closest to Saturn have to move fastest. In the inner main rings, they can race around the planet at more than 20 kilometers per second. Farther out, where Saturn's gravity is weaker, the particles move more slowly. This difference creates the layered motion of the rings, with inner lanes sliding past outer lanes like separate streams around the same world. But Saturn's gravity alone does not explain the ring's shape. Saturn also has more than 140 known moons, and several of them act like sculptors. Some moons orbit near the rings. Some orbit inside gaps. Some orbit just beyond the ring edges. As they pass, their gravity tugs on nearby particles, pulling them slightly inward or outward, speeding them up or slowing them down by tiny amounts. Over one orbit, the tug is small. Over thousands or millions of orbits, it can carve structure into the rings. The Cassini division, the dark gap between Saturn's A ring and B ring, is about 4,800 kilometers wide. One of the main influences on that gap is the moon Mimas. Mimas orbits Saturn farther out, but its gravity creates a repeated pattern called an orbital resonance. A resonance happens when two orbits line up in a repeating rhythm. In this case, particles in the Cassini division region can orbit Saturn twice for every one orbit of Mimas. That repeated tug comes again and again at the same point in their path, slowly disturbing those particles until the region becomes depleted. Other moons create more visible cuts. Pan, a small moon only about 28 kilometers across, orbits inside the Encke gap in Saturn's A ring. Its gravity clears a narrow path through the ring material, leaving a gap about 325 kilometers wide. Daphnis, an even smaller moon, moves inside the Keeler gap and raises tiny vertical waves along the gap edges. In Cassini images, those waves look like little ridges and shadows cast across the rings. Then there are shepherd moons. Prometheus and Pandora help shape the narrow F ring, one of Saturn's outer rings. Their gravity keeps tugging at the ring's particles, making braided patterns, clumps, streamers, and sharp edges. Prometheus, especially, dives close to the F ring and pulls out strands of material as it moves around Saturn. The rings survive through this constant negotiation. Gravity pulls inward. Orbital motion carries particles around. Collisions flatten and organize the swarm. Moons carve gaps, sharpen edges, and send waves through the ice. Even collisions help maintain the thinness of the rings. When particles bump into each other, they tend to lose some vertical motion. Over time, those small impacts help settle material into a flatter plane, like shaking a box of loose objects until they spread into a layer. So the rings are organized, but they are never still. They are held together by motion. They are shaped by moons. They are softened and flattened by collisions. They are guided by repeated gravitational rhythms that have been playing around Saturn for enormous stretches of time. And this is where the story becomes more unsettling. The same forces that make the rings beautiful also make them vulnerable. A moon that shapes a gap can disturb particles. A collision that creates dust can make smaller grains easier to move. A tiny fragment that becomes charged can stop behaving like an ordinary piece of ice and start responding to Saturn's magnetic field. The rings stay in place because of balance. But balance can be broken. And around Saturn, some of the smallest pieces have already begun following a path that leads downward. The smallest pieces in Saturn's rings do something the larger chunks cannot do as easily. They become electrically charged. A boulder-sized piece of ice can keep orbiting Saturn mostly under the control of gravity. It behaves like a tiny moon. It follows a path around the planet, collides occasionally, and remains part of the broad swarm. But a dust grain is different. A dust grain has very little mass. It can be pushed, heated, charged, and redirected by forces that would barely affect a larger object. Around Saturn, those tiny grains are exposed to sunlight, high-energy particles, and plasma. Plasma is gas that has been energized so strongly that electrons separate from atoms. That creates a mixture of charged particles. Saturn's environment is full of this kind of material, especially because its moon Enceladus sprays water vapor and icy grains from cracks near its south pole. Some of that material becomes ionized, meaning it gains or loses electrons and becomes electrically charged. The rings sit inside this active magnetic environment. Saturn has a magnetic field, like Earth does. It is generated deep inside the planet, probably by layers of electrically conducting fluid moving under pressure. At Saturn's cloud tops, the magnetic field is weaker than Earth's surface field, but it stretches far into space and forms a huge magnetic bubble around the planet. That magnetic field rotates with Saturn. Saturn spins quickly, completing one rotation in about 10.5 hours. As it spins, its magnetic field sweeps through the space around it, interacting with plasma, dust, and charged particles. For a tiny, icy grain, this changes everything. Once that grain becomes charged, it no longer responds only to gravity. It also responds to electromagnetic forces. These are the same basic forces that make a compass needle align with a magnetic field, or make charged particles spiral around magnetic field lines. A magnetic field line is an invisible path showing the direction of the magnetic field. Around Saturn, these lines arc out from one region of the planet and curve back into another. Charged particles tend to move along them, spiral around them, or become guided by them. So when a tiny grain from the rings becomes charged, Saturn's magnetic field can begin to redirect it. The particle may start to drift away from its original orbit. It can be pulled out of the flat ring plane. It can follow magnetic pathways downward towards Saturn's upper atmosphere, where the planet's hydrogen-rich air begins to catch and absorb incoming material. This is the invisible pull downward. From Earth, the rings still look calm. Through a telescope, they remain pale and graceful, a thin line of reflected sunlight around the planet. Nothing about the view reveals that some of the smallest icy grains are being removed, guided along magnetic routes, and delivered into Saturn's atmosphere. But above Saturn, the process is active. The rings are losing material in streams too faint and spread out to see with ordinary eyes. These streams can connect certain parts of the rings to certain latitudes on Saturn, almost like invisible threads tying the ring system to the planet below. When the particles enter the upper atmosphere, they change the chemistry there. Water from the rings can interact with Saturn's ionosphere, the electrically charged upper layer of the atmosphere. It can affect the glow of hydrogen, alter patterns of charged particles, and leave traces that scientists can detect with specialized instruments. That is how something hidden becomes measurable. The falling material does not arrive like rain on Earth, with drops striking a surface. Saturn has no solid surface where rain can splash or pool. Instead, the material enters layer after layer of gas. It breaks apart, reacts, spreads, and becomes part of the planet's atmosphere. The rings are feeding Saturn from above. Grain by grain, charged particle by charged particle. Some of the ice that once circled the planet becomes part of the planet itself. This is what makes the disappearance so strange. The rings are vanishing through a process too subtle for the human eye and too slow for a human lifetime. Yet it is steady enough to matter across planetary time. Saturn's crown is leaking, and the leak has a name. Scientists call this process ring rain. It sounds almost gentle, but the name describes one of the strangest exchanges happening anywhere in the solar system. Icy material from Saturn's rings is leaving orbit and falling into the planet's atmosphere. This rain begins high above Saturn, in the thin ring plane where countless grains of water ice circle the planet. Some of those grains are tiny enough to be changed by sunlight, plasma, and Saturn's magnetic field. Once they become electrically charged, they can be guided away from the rings and down along magnetic field lines toward the planet below. Saturn's magnetic field acts like an invisible structure around the planet. It reaches outward into space, loops through the ring system, and connects back to Saturn's upper atmosphere. Charged particles can move along those paths, spiraling around them as they travel. So when icy ring material becomes charged, some of it follows those invisible routes downward. From far away, nothing dramatic appears to happen. The rings still shine. Saturn still turns slowly beneath them. The planet still looks calm and distant. But in Saturn's upper atmosphere, the falling material leaves chemical fingerprints. One of the clearest clues came from infrared observations made with the Keck telescope in Hawaii. Infrared light is light beyond the red end of what human eyes can see. It is useful for studying heat, glowing gases, and certain chemical reactions in planetary atmospheres. When scientists examined Saturn in infrared, they found bright and dark bands in the planet's upper atmosphere. These bands lined up with places where Saturn's magnetic field connects the rings to the planet. That pattern suggested the rings were sending material down into specific regions of Saturn's atmosphere, rather than simply losing material randomly into space. The falling water from the rings affects Saturn's ionosphere. The ionosphere is the upper part of an atmosphere, where sunlight and energetic particles strip electrons from atoms and molecules, creating electrically charged gas. Earth has an ionosphere too. It helps reflect some radio waves and is involved in auroras. Saturn's ionosphere is much farther away, colder, and shaped by the planet's powerful magnetic environment. When ring water enters that region, it changes the balance of charged particles. Water molecules from the rings can interact with hydrogen ions in Saturn's upper atmosphere. They can reduce certain kinds of glowing emissions and create the banded patterns scientists observed. In other words, the rings are leaving marks on Saturn's sky. This makes ring rain different from the kind of rain we know on Earth. On Earth, Rain falls from clouds made of liquid water droplets or ice crystals. It passes through air, reaches the ground, flows into rivers, and returns to the ocean. Saturn has no solid ground waiting under the clouds. It is a gas giant, made mostly of hydrogen and helium, with deeper layers that become hotter and more compressed as you move inward. So ring rain falls into atmosphere. It enters gas. It changes chemistry. It becomes part of Saturn. The ice that once reflected sunlight as part of the rings is absorbed into the world beneath it. That is what makes the process so unsettling. The rings are beautiful because they look separate from Saturn, like a bright crown floating around the planet. But ring rain shows that the rings and the planet are connected. Material is moving from one to the other through invisible magnetic paths. The ring system is feeding Saturn, and it has likely been doing this for a very long time. Across one human lifetime, the loss is impossible to see by simply looking through a telescope. Across the lifetime of a civilization, the rings still appear mostly unchanged. But across millions of years, the slow flow begins to matter. A dust grain becomes charged. A particle leaves orbit. A stream follows a magnetic field line. A trace of water enters Saturn's upper air. Then another, then another. The rings are disappearing through countless tiny events that add up on a planetary clock. And once scientists understood that Saturn was receiving material from above, the story became even stranger. Because this was no longer just a delicate ring system losing dust. It was a giant planet slowly consuming the thing that made it famous. The image sounds almost impossible. A planet eating its own rings. Saturn is not alive, of course. It has no mouth, no surface, no hunger. But physically, that is what the measurements suggest. Material that once circled the planet as part of its bright ring system is slowly leaving orbit and entering Saturn's atmosphere. The process is quiet. There is no single collapse, no sudden breaking apart, no moment when the rings fall all at once. Instead, Saturn is taking them in through countless tiny streams of ice, dust, water molecules, and charged particles. A small grain leaves the ring plane. A molecule follows a magnetic field line. A faint flow enters the upper atmosphere. Then the process repeats again and again, too slowly for human eyes, but steadily enough to matter across millions of years. One estimate described the loss as roughly enough water products to fill an Olympic-sized swimming pool every half hour. That comparison is strange because Saturn's rings are enormous. The main ring system spreads across hundreds of thousands of kilometers. A swimming pool feels tiny beside that. But the comparison becomes unsettling when time is added. Every half hour, every day, every year, across 1 million years, even a gentle leak becomes a major loss. An Olympic-sized swimming pool holds about 2.5 million liters of water. On Earth, that would be a huge amount of liquid. Around Saturn, it is only a small part of a vast ring system, made mostly of ice. But if that much water-related material keeps draining from the rings again and again, the loss becomes difficult to ignore. And ring rain may be only part of the story. Near the end of the Cassini mission, the spacecraft made a series of daring passes between Saturn and the inner edge of the rings. This final phase began in 2017 and was called the grand finale. Cassini had spent more than 13 years orbiting Saturn, studying the planet, its moons, and its rings. Then, before the spacecraft was deliberately sent into Saturn's atmosphere, it flew through a region no spacecraft had ever explored so closely. During those final orbits, Cassini detected material falling from the rings towards Saturn's equator. This was separate from the ring rain guided by magnetic field lines into higher latitudes. It showed that ring material could also move inward from the ring system and enter the planet closer to its middle regions. That made the loss feel larger and more complicated. Saturn was receiving material along magnetic paths. Saturn was also receiving material from the inner rings. The planet was being fed from above in more than one way. Cassini found that the falling material was chemically complex. It included water, but also organic molecules and tiny grains. Organic molecules are carbon-bearing compounds. They do not automatically mean life. In space science, the word organic often refers to chemistry built around carbon, hydrogen, oxygen, nitrogen, and related elements. Around Saturn, those materials can come from dust, icy particles, radiation chemistry, and material processed over time in the ring system. So the rings are not simply pure ice falling into a planet. They are a mixture: bright water ice, dust, charged particles, carbon-rich material, tiny fragments shaped by sunlight, impacts, and Saturn's magnetic environment. As this material falls inward, it changes Saturn's upper atmosphere. It can affect charged layers of gas, alter chemical reactions, and leave traces in specific bands around the planet. Saturn is slowly being marked by the disappearance of its own rings. That is the deeper image. The rings are not separate decoration. They are connected to Saturn's atmosphere, Saturn's magnetic field, Saturn's moons, and Saturn's future. A piece of ice can orbit for ages, shining in the ring plane. Then a tiny disturbance changes its path. It becomes charged. It drifts. It collides. It is pulled inward. Eventually, it stops being part of the rings and becomes part of Saturn. The planet keeps turning. The rings keep shining. But the exchange continues. And once a planet is steadily receiving pieces of its own ring system, the mystery becomes larger than the process itself. How long can the rings survive while this keeps happening? The scale of the loss is difficult to feel because the clock is so large. To a human observer, Saturn's rings look unchanged. A person could study the planet for an entire lifetime and still see the same broad bands of ice circling the planet. Even across a century of telescope images, the rings still appear bright, wide, and stable. But planetary time works differently. The ring rain estimate suggests Saturn's rings may have less than 300 million years left. When Cassini measurements of material falling towards Saturn's equator are included, the possible lifetime becomes even shorter, perhaps less than 100 million years. Those numbers sound enormous. 100 million years is longer than the time since the dinosaurs disappeared. The asteroid impact that ended the age of non-avian dinosaurs happened about 66 million years ago. Since then, mammals diversified, primates evolved, humans appeared, cities were built, telescopes were invented, and spacecraft crossed the solar system. So if Saturn's rings lasted another 100 million years, they would still outlive almost everything familiar to us. They would outlive nations. They would outlive languages. They would outlive every building now standing on Earth. They might still be there long after the continents have shifted into new positions, after new mountain ranges have risen, after Earth's current species have been replaced by future life we cannot picture. But compared with Saturn, 100 million years is brief. Saturn is about 4.5 billion years old. If its full lifetime so far were compressed into one calendar year, 100 million years would be only about 8 days. 300 million years would be less than a month. That is the unsettling scale. For humans, the rings seem almost eternal. For Saturn, they may be a passing season. The rings are being drained too slowly for us to watch in real time, yet quickly enough that they cannot be treated as permanent on the planet's full timeline. Ring rain is not a sudden disaster. It is a slow countdown measured in grains, molecules, charged particles, and invisible streams entering the atmosphere. A small loss becomes meaningful because it never stops. Half an hour becomes a pool of water products. A day becomes dozens of pools. A year becomes thousands. A million years becomes an amount large enough to change the ring system. Then 100 million years becomes a future where the bright rings may be much thinner, darker, or partly gone. This is how cosmic disappearance often works. It does not always arrive as an explosion. Sometimes it arrives as a leak. A glacier can retreat by meters each year and still transform a landscape. A coastline can erode grain by grain and still move inland. A star can burn hydrogen steadily for billions of years and still be spending fuel every second. Saturn's rings are following their own version of that slow pattern. They shine because they are made of ice. They fade because that ice is being disturbed, charged, darkened, and lost. And every orbit around Saturn gives the process more time to continue. The rings do not need to collapse tomorrow to be temporary. They only need a future where the loss keeps adding up. That future changes the way Saturn looks in the mind. It is easy to imagine the rings as part of the planet, as if Saturn formed with them and will always carry them. But the numbers suggest something stranger. The rings may be only a chapter in Saturn's life. A bright chapter. A famous chapter. The chapter we happen to arrive in time to see. And if a chapter can end, it must also have begun. The rings may be disappearing now, but they were also created at some earlier moment. They came from somewhere. Ice had to be placed in orbit. A structure had to form. A system this wide and delicate had to be assembled around a planet that was already ancient. So the countdown points backward as well as forward. If Saturn's rings are temporary, then the deeper mystery is when Saturn first received its crown. If Saturn's rings are truly fading, their age becomes even more important. They may be much younger than Saturn itself. Saturn formed about 4.5 billion years ago, during the same early era that produced the rest of the solar system. The young sun was surrounded by a wide spinning disk of gas and dust. Inside that disk, solid grains stuck together, larger bodies formed, and the giant planets gathered enormous envelopes of hydrogen and helium. Saturn grew in that ancient disk. Its core formed first. Then its atmosphere expanded around it. Over time, it became the second largest planet in the solar system. with enough gravity to hold dozens of moons and shape a huge region around itself. The rings, however, may have arrived much later. Some interpretations of Cassini data have placed Saturn's bright main rings somewhere around 100 million to 400 million years old. That is still an immense span of time. A ring system 100 million years old would have formed while dinosaurs still walked on Earth. A ring system 400 million years old would reach back toward the Devonian period, when early forests were spreading across land and many animals still lived mainly in the oceans. But compared with Saturn, even 400 million years is recent. Saturn had already existed for more than 4 billion years. Its clouds had already been circling the planet for ages. Its interior had already been compressed under unimaginable pressure. Its large moon Titan had already formed. Enceladus, Mimas, Tethys, Dione, Rhea, and other moons were already moving around the planet in their long gravitational dance. Then, if the young ring interpretation is right, the bright rings appeared late, long after Saturn formed, long after Earth's first oceans, long after single-celled life had changed this planet, long after the solar system had settled into the basic arrangement we know. That means the Saturn we recognize may be a recent version of Saturn. The planet did not need its rings to exist. It did not need them to become massive, cold, stormy, or complex. Saturn was already Saturn before the rings became bright enough to define it in human imagination. Cassini helped make this possibility more serious because it measured the rings in detail no telescope on Earth could match. The spacecraft arrived at Saturn in 2004 and spent more than 13 years orbiting the planet. During its final months in 2017, Cassini flew repeatedly between Saturn and the inner edge of the rings, passing through a narrow region that had never been explored by a spacecraft before. Those final passes helped scientists estimate the mass of the rings. Mass matters because it helps reveal age. A heavier ring system can survive longer and can hold more old material. A lighter ring system is easier to drain, easier to pollute, and easier to imagine as a younger structure. Cassini also showed that the rings are bright and rich in water ice. That brightness is part of the age argument. Space is dusty. Tiny micrometeoroids strike objects throughout the solar system. Over time, dark material should collect in a ring system, like soot settling onto snow. If the rings had been exposed for billions of years, many scientists expected them to look darker than they do. Instead, the main rings are still brilliantly reflective. That clean appearance has been used as evidence that the rings may be young enough to have avoided collecting too much dark debris. So the picture becomes strange. Saturn is ancient. The rings look fresh, and the rings are falling. Together, those facts make Saturn feel less like a fixed object and more like a planet passing through a temporary stage. For most of Saturn's life, the planet may have had no broad, bright rings at all. It may have looked more like a pale gas giant surrounded by moons and faint debris, without the wide icy bands that now make it instantly recognizable. Then, sometime in the relatively recent past, something changed. A moon may have shattered. A comet may have been torn apart. An icy body may have crossed too close to Saturn and been pulled into fragments. Whatever happened, If the young ring interpretation is right, it happened after billions of years had already passed. The Saturn we know may have arrived late, and before that, there may have been another Saturn, quieter, darker, and missing the crown we now mistake for permanent. Imagine Saturn without its rings. The planet would still be enormous. It would still be the second largest planet in the solar system, more than 120,000 kilometers wide at the equator. It would still contain about 95 times Earth's mass. It would still spin so quickly that one day on Saturn lasts only about 10.5 hours, making the planet bulge outward at its middle. Its clouds would still circle in pale bands of hydrogen, helium, ammonia ice, and deeper storm layers hidden far below what telescopes can see. Its winds would still race around the planet at hundreds of meters per second. Its North Pole would still hold the strange hexagon discovered by Voyager in the early 1980s, a six-sided jet stream wider than Earth itself. Each side of that hexagon is roughly 14,500 kilometers long, and the pattern has persisted for decades, turning with Saturn's atmosphere like a giant geometric storm. Saturn would still have its moons. Titan would still orbit far outside the main rings, larger than the planet Mercury, wrapped in a thick nitrogen atmosphere with methane clouds, methane rain, rivers, lakes, and dark organic dunes. Enceladus would still shine as a small icy moon, only about 500 kilometers across, spraying water vapor and ice grains from cracks near its south pole. Mimas would still look like a battered ball of ice, marked by the huge Herschel crater that makes it resemble a small broken world. Saturn would still have a magnetic field. That field would still stretch into space, trapping charged particles and shaping a vast magnetic environment around the planet. It would still interact with the solar wind, the stream of charged particles flowing outward from the sun. It would still help create auroras near Saturn's poles, glowing curtains of ultraviolet light high above the cloud tops. A ringless Saturn would still be a powerful, complex, beautiful world. But it would feel different to us. Because in the human imagination, Saturn's identity is tied almost completely to its rings. When people picture Saturn, they usually picture the wide, bright bands first. The planet and the rings arrive together in the mind as one shape, one symbol, one familiar icon of space. That image is so strong that it can make the rings feel like part of Saturn's body. But the rings are separate. They are orbiting debris. They are ice and dust moving around the planet. And if the young ring interpretation is right, Saturn existed for most of its life before those bright rings appeared. For billions of years, Saturn may have circled the Sun as a giant planet, without the crown we now use to recognize it. Earth changed from a molten young planet into an ocean world. Early life appeared. Oxygen slowly built up in the atmosphere. Continents formed, split, and moved. Animal life evolved in the oceans. Plants spread across land. Forests rose. Insects, amphibians, reptiles, and mammals all appeared across deep time. Through most of that story, Saturn may have looked far less dramatic than it does now. The solar system itself would have had a different face. A traveler looking at Saturn long ago might have seen a pale giant with moons, storms, and perhaps faint dusty material around it. but without the brilliant wide rings that later became its signature. The night sky of Saturn's moons would have looked different. Titan, Enceladus, and the other moons may have orbited under a darker, emptier Saturn. Then something changed. Somewhere in Saturn's past, ice had to be placed into orbit in enormous quantities. The rings contain enough material to form a small moon, and most of it is water ice. That material had to come from somewhere. It may have come from a moon that wandered too close, a comet that broke apart, or a collision that shattered an icy body into fragments. A ring system this wide does not appear quietly from nothing. It suggests disruption, a lost moon, a torn object, a violent event softened by time into one of the most beautiful sights in the solar system. So Saturn before the rings leads naturally to the deeper origin story. If the planet gained its crown late, then something near Saturn had to be destroyed. The most haunting possibility is that Saturn's rings began as a lost world. The rings may be made from pieces of a comet, an asteroid, or an icy moon that broke apart before it could fall into Saturn. That idea changes the way the rings feel. They stop being only a beautiful feature around the planet and become wreckage, spread into a bright circle by gravity. The material fits that story. Saturn's main rings are made mostly of water ice. That bright ice reflects sunlight so well that the rings shine across more than 1 billion kilometers of space. A disrupted icy moon could provide exactly that kind of material. If a small moon with an icy crust or icy interior were shattered near Saturn, its fragments could spread out into the ring plane and form the broad bands we see today. The amount of material in the rings is large, but it is small compared with a major moon. The total mass of Saturn's rings is often compared to a moon only a few hundred kilometers across. Mimas, one of Saturn's small inner moons, is about 396 kilometers wide and is sometimes used as a rough comparison for the scale of ring material. Mimas itself is famous for its huge Herschel crater, which is about 130 kilometers across, nearly 1/3 of the moon's diameter. A body in that size range would be tiny compared with Titan, which is larger than Mercury, but large enough to create an enormous ring system if it were broken apart. That broken body could have reached its dangerous path in several ways. A collision may have struck it, changing its orbit. A passing comet may have disrupted the moon system. Gravitational pulls from other moons may have slowly shifted its path over time. In a system like Saturn's, small changes can build over millions of years. A moon does not need to be thrown instantly into the planet. Its orbit can be altered gradually, tug by tug, until it enters a region where Saturn's gravity becomes dangerous. The Saturn system is crowded with moving bodies. Titan orbits far out, wrapped in its thick orange atmosphere. Rhea, Dione, Tethys, Enceladus, Mimas, and many smaller moons move closer in. Their gravity interacts constantly. Some moons are locked in resonances, repeating orbital rhythms where one moon tugs another at regular intervals. Over very long periods, those repeated tugs can reshape orbits, move moons inward or outward, and create instability. A moon that once orbited safely could be pushed into a more dangerous region. A comet from the outer solar system could also have entered Saturn's realm. Comets are icy bodies left over from the formation of the planets. Many spend most of their lives far from the Sun, then occasionally fall inward on long stretched orbits. If one passed too close to Saturn, the planet's gravity could tear it apart, scattering ice and dust into orbit. An asteroid would bring more rocky material, so a shattered icy moon or comet better matches the ring's bright water ice composition. But the broader idea is the same. Something entered the wrong place at the wrong time, and Saturn's gravity turned it into debris. Over time, that debris would flatten. Fragments on tilted orbits would collide with other fragments. Those collisions would cancel out some of the up and down motion, gradually settling the material into a thin disk around Saturn's equator. Pieces closer to Saturn would orbit faster. Pieces farther out would orbit more slowly. Moons would carve gaps, create waves, and shape the edges. After enough time, the violence would become hidden. The sharp fragments would grind down. The debris would spread. The wreckage would turn into rings. This is one of the strangest parts of Saturn's story. The calm, beautiful structure we see today may have started with destruction. A moon, comet, or icy body may have been broken apart so completely that its remains became one of the most famous sights in the solar system. And there is a specific invisible boundary around Saturn where that kind of destruction becomes possible. The invisible boundary is called the Roche limit. It is named after the French mathematician Edouard Roche, who studied tidal forces in the 1800s. A tidal force happens when gravity pulls harder on one side of an object than the other. On Earth, the moon's gravity raises tides in the oceans because the near side of Earth feels a slightly stronger pull than the far side. Near Saturn, that same idea becomes much more extreme. Saturn is nearly 95 times more massive than Earth. Its gravity field is powerful enough to control moons, rings, dust, plasma, and spacecraft across a vast region of space. If a small moon moves too close, Saturn pulls more strongly on the side facing the planet than on the side facing away. The difference between those pulls stretches the moon. At a safe distance, the moon's own gravity can hold it together. Its rocks and ice remain bound. Its surface stays mostly intact. It keeps orbiting as a single world. Closer in, the stress grows. The near side is tugged downward toward Saturn. The far side lags behind. The moon is squeezed and stretched again and again. Every moment it remains too close. If the tidal stress becomes stronger than the moon's self-gravity, the moon can no longer hold itself together. It begins to break. Cracks can spread through its icy crust. Loose material can lift away. Larger fragments can separate from the main body. Eventually, the moon may be torn apart into a stream of debris. That debris does not simply fall straight into Saturn. The fragments still have sideways orbital motion. They keep moving around the planet. The pieces closest to Saturn move faster. The pieces farther out move more slowly. Over time, the debris spreads around the planet, stretching into a long arc, then a partial ring, then a complete band of orbiting material. This is how a moon can become a ring. The Roche limit depends on the density and strength of the smaller body. A loose icy moon can be disrupted more easily than a dense rocky object. A solid body with internal strength can survive somewhat closer than a weak rubble pile. But the basic idea remains the same. There is a distance where Saturn's gravity stops being only the force that holds a moon in orbit and becomes the force that pulls it apart. Saturn's main rings sit inside the region where large, loose moons would struggle to survive. That is one reason the ring system makes physical sense. The material is close enough to Saturn that it can remain spread out as countless fragments instead of gathering easily into one larger moon. Farther away, outside the strongest tidal zone, debris can clump together over time. Closer in, Saturn keeps the material separated, stirred, and flattened into a thin disk. The rings are therefore tied to a boundary of destruction. They orbit in a place where gravity can preserve debris as debris. This gives the ring system a darker origin. If an icy moon once crossed too far inward, Saturn's gravity could have taken it apart. The same planet that now holds the rings in a graceful circle may have first created them by tearing a smaller world open. It would have been a slow catastrophe by human standards, or perhaps a violent one if the moon entered the region quickly after a collision or orbital disturbance. Either way, the result would be the same. Ice that once belonged to one body would become billions of separate bodies. Some fragments would collide. Some would grind into dust. Some would spread into lanes. Some would be shaped by moons and resonances. And over time, the broken moon would lose its original form completely. No mountains, no craters, no single surface. Only ice, orbit, shadow, and light. That is why the rings can look peaceful while carrying the memory of violence. The Roche limit explains how beauty can form from destruction, and why Saturn's brightest feature may be the remains of something that came too close. If an icy moon broke apart near Saturn, the first moments would not have looked like the rings we see today. There would have been chaos. Large fragments would have separated from the original body. Smaller pieces would have sprayed outward. Ice blocks, dust, and shattered material would have entered slightly different orbits around Saturn. Some pieces would have moved closer to the planet and sped up. Others would have moved farther out and slowed down. The broken moon would have stretched into a long stream. At first, the debris may have looked uneven, clumped and violent, more like wreckage than a ring. Pieces would collide with one another. Some collisions would be gentle, like ice brushing ice. Others would be powerful enough to break larger chunks into smaller fragments. Every impact would change the motion of the debris a little. Over time, Saturn's gravity would spread the material around the planet. A fragment close to Saturn completes an orbit faster than one farther away. This difference in orbital speed would pull the wreckage into a longer and longer arc. Eventually, that arc could wrap completely around the planet, forming a ring of debris where one moon or icy body had once existed. But the ring would still need to flatten. A shattered moon would not begin as a perfectly thin sheet. Some fragments would move slightly above the ring plane. Others would move below it. Some would follow tilted paths. Some would cross the paths of other fragments. Collisions would slowly erase that disorder. When two icy pieces collide, they exchange energy and momentum. Momentum is the motion an object carries because of its mass and speed. If enough collisions happen, the up and down motion gets reduced. the debris settles into a flatter and flatter disk around Saturn's equator. This is the same basic reason many planetary systems form disks. When material orbits a central object, random tilted motions tend to cancel out through collisions. The motion that survives is the smooth motion around the center. Around a young star, this can help create a flat disk where planets form. Around Saturn, it could help broken icy material settle into a thin ring. The violence becomes organized. The wreckage becomes structure. The pieces that once belonged to a single body become lanes, gaps, and bands. Tiny grains scatter light. Larger chunks cast shadows. Moons tug on the edges. Resonances carve openings. Repeated collisions grind some material down into dust, while other fragments remain as larger icy pieces. After enough time, the catastrophe becomes hard to recognize. There is no obvious ruin left. No broken moon with half a surface missing. No cratered remnant floating beside the rings. Only a bright, flat system of ice circling Saturn with such grace that it looks intentional. That is part of what makes Saturn's rings so haunting. They may preserve the memory of destruction in one of the calmest forms possible. A lost moon, comet, or icy body may have been pulled apart, ground down, spread out, and transformed into the most beautiful structure in the solar system. The rings are not silent because nothing happened. They are silent because time has smoothed the event. Sharp fragments became rounded. Clouds of debris became bands. A dangerous orbit became a shining disk. From Earth, we see the finished shape. We do not see the fracture, the first collisions, or the slow spreading of debris around Saturn. We see the aftermath after gravity has had time to arrange it. And that makes the rings feel almost deceptive. They look peaceful. They may have begun with violence. They look permanent. They may be temporary. They look like decoration. They may be the remains of a destroyed world. But this origin story is difficult to prove from far away. Telescopes can show the ring's brightness, shape, and position. They can reveal gaps and broad structure. But they cannot easily tell us the ring's true mass, exact age, detailed composition, or how much material is falling into Saturn. To understand whether the rings are young, old, fading, or born from a broken moon, scientists needed more than distant images. They needed to send a spacecraft close enough to Saturn to inspect the rings from within the system itself. To study Saturn's rings properly, scientists needed to go there. Telescopes had already shown the rings from Earth. Voyager 1 and Voyager 2 had flown past Saturn in 1980 and 1981, revealing fine structure, narrow ringlets, spokes, waves, and moon-carved gaps. But flybys are brief. A spacecraft passes once, gathers what it can, then keeps moving. Cassini was different. Cassini was built to stay. The spacecraft launched from Cape Canaveral on October 15, 1997. It was one of the largest and most complex planetary spacecraft ever sent into deep space, about the size of a small bus, carrying cameras, spectrometers, dust detectors, plasma instruments, magnetometers, radar, and radio science equipment. It did not travel straight to Saturn. Saturn is too far away, and the spacecraft was too heavy for a direct launch. Cassini used gravity assists, borrowing energy from planets as it passed them. It flew by Venus twice, Earth once, and Jupiter once, before finally reaching Saturn. On July 1st, 2004, Cassini fired its main engine and entered orbit around Saturn. That moment changed the study of the planet completely. For the first time, humanity had a spacecraft living inside the Saturn system, circling the planet again and again, watching the rings under changing angles of sunlight, moving past moons, sampling particles, measuring magnetic fields, and tracking how everything interacted. Cassini orbited Saturn from 2004 to 2017, more than 13 years. During that time, it studied Saturn's storms, Saturn's magnetosphere, Saturn's rings, and Saturn's moons. It watched the seasons change as Saturn slowly moved around the Sun. It saw shadows from the rings fall across the planet. It observed the strange hexagon at Saturn's North Pole. It sent the Huygens probe to Titan, where it landed on January 14, 2005, becoming the first spacecraft to touch the surface of a moon in the outer solar system. But for the rings, Cassini was especially important because it could see them as a physical system. It could measure their brightness at different wavelengths. It could see dust. It could watch tiny moons disturb ring edges. It could observe waves passing through the rings like ripples through a frozen pond. It could study the spokes, those ghostly radial markings that appear and fade across the B ring. It could look at the rings from above, below, and nearly edge on. Cassini showed that the rings were not a flat decoration. They were active, dynamic, layered, a place where gravity, dust, sunlight, magnetic fields, and small moons were constantly shaping the ice. Then came the final phase. In 2017, after years of discoveries, Cassini was almost out of fuel. Engineers could not risk leaving the spacecraft uncontrolled near moons like Titan or Enceladus, where future scientists might search for signs of life or habitability. So they chose a controlled ending. Cassini would dive into Saturn's atmosphere. Before that final plunge, it performed a daring sequence called the Grand Finale. Starting in April 2017, Cassini flew repeatedly through the narrow gap between Saturn and the inner edge of the rings. This gap was only about 2,400 kilometers wide. For a spacecraft moving tens of thousands of kilometers per hour, that was an incredibly precise path. 22 times, Cassini passed between the planet and the rings. No spacecraft had ever flown there before. During these dives, Cassini measured Saturn's gravity field with extreme precision. Tiny changes in the spacecraft's motion allowed scientists to estimate the mass of the rings. It also detected material falling from the rings into the planet, including water, dust, and carbon-rich compounds. This was not a distant photograph anymore. This was direct measurement. Cassini was moving through the space where Saturn's atmosphere, magnetic field, and ring system meet. It was helping reveal how heavy the rings are, what they are made of, and how material is being lost. On September 15, 2017, Cassini entered Saturn's atmosphere and burned up, sending data until the signal vanished. Its mission ended inside the planet it had studied for 13 years. But the measurements remained. And those measurements turned Saturn's rings from a beautiful image into something much more physical. A structure with mass, dust, chemistry, age, motion, and loss. The next mystery was hidden in their brightness. Cassini revealed something that made Saturn's rings even harder to explain. They are bright, almost too bright. The main rings are made mostly of water ice, and clean water ice reflects sunlight extremely well. That is why the rings shine so clearly from more than 1 billion kilometers away. Even through small telescopes on Earth, they can look pale, crisp, and luminous against the darkness around the planet. This brightness became one of the strongest clues in the age mystery. Space is dusty. Tiny micrometeoroids move through the solar system all the time. A micrometeoroid is a very small piece of rock, metal, or dust, often smaller than a grain of sand, traveling at high speed. These particles come from comets, asteroids, collisions, and leftover debris from the formation of the solar system. They strike moons, they strike asteroids, they strike spacecraft, and they strike Saturn's rings. Each impact adds a little dark material or changes the ice already there. Over long spans of time, that should matter. If a bright, icy surface keeps collecting dark dust for billions of years, scientists expect it to become less clean, less reflective, and more polluted. The comparison is simple. Fresh snow looks bright because it reflects sunlight. But if soot, dirt, and ash settle onto it day after day, it slowly darkens. The snow may still be snow, but it no longer looks fresh. Saturn's rings have been treated in a similar way. If the rings had been around since Saturn formed, about 4.5 billion years ago, they should have collected an enormous amount of dark material. Billions of years of micrometeoroid impacts should have changed their color and brightness. The rings should look more contaminated. Yet the main rings still look rich in clean water ice. That clean appearance helps support the idea that the rings are relatively young. Cassini made this argument sharper because it studied the rings in many wavelengths of light. Different wavelengths reveal different properties. Visible light shows brightness and color. Infrared light can reveal ice features and temperature. Ultraviolet measurements can help identify small particles and chemical patterns. Together, these observations showed that Saturn's main rings are dominated by bright, icy material. The B ring, the densest and brightest part of the system, is especially striking. It reflects so much sunlight that it can appear almost white in some spacecraft images. The A ring is also bright, with detailed waves and gaps shaped by nearby moons. The C ring is darker and more transparent, showing that different regions have different histories and different amounts of material. That variation matters. The rings are not all equally clean. Some regions are darker, some are denser, some are more transparent, some contain more dust. But overall, the main ring system is still bright enough to raise the same problem. How can something exposed to space for billions of years still look so clean? That question helped push scientists toward a younger age estimate. If the rings are only 100 million to 400 million years old, then they have had far less time to collect dark pollution. Their brightness becomes easier to understand. They are icy and reflective because they have not been exposed long enough to become heavily darkened. On Earth, 100 million years is almost impossible to hold in the mind. It reaches back before humans, before grasslands looked the way they do now, before the last dinosaurs disappeared. But beside the age of Saturn, it is recent. It is a late chapter. So the ring's brightness seemed like a clock. Clean ice suggested youth. Darkened ice would have suggested age. Cassini gave scientists a way to read that clock more carefully than ever before. But clocks can be misleading when the system they measure is active. The rings are not passive sheets of ice waiting quietly for dust to settle. They are orbiting, colliding, spreading, charging, and losing material. Micrometeoroid impacts do more than add dirt. They can blast material apart. They can vaporize particles. They can create charged grains that leave the rings entirely. And that makes the next part of the story more complicated. The rings may look clean because they are young. Or they may look clean because Saturn is better at removing the dirt than scientists once thought. The clean ring argument sounds simple at first. Bright ice suggests young ice. Darkened ice suggests old ice. But newer research has made that clock harder to read. The key problem is what happens when micrometeoroids hit the rings. For a long time, the basic idea was that tiny dark particles would strike the icy ring material and leave contamination behind, slowly coating the rings over millions or billions of years. That would make the rings darker with age. But recent computer modeling suggests the impacts may behave in a more complicated way. Micrometeoroids do not gently settle onto the rings like dust on a shelf. They hit at extremely high speeds. Some can strike at tens of kilometers per second. At those speeds, even a tiny grain carries enough energy to heat, break, and vaporize material at the impact site. Vaporize means the material changes into gas. A micrometeoroid striking icy ring particles can create a burst of vapor, fragments, and electrically charged material. Instead of leaving all of its dark material behind on the ring, part of the impact debris may be removed from the ring system. Some of it can become charged. Some can be guided by Saturn's magnetic field. Some can be pulled toward Saturn. Some can be thrown out of the rings and lost into space. That changes the meaning of the ring's brightness. If dark incoming material is efficiently removed after impact, then clean-looking rings do not automatically have to be extremely young. They may be older than they appear, because the ring system has a way of cleaning itself, at least partly. The image is almost like snow in a windy place. Fresh snow can stay bright when new dirt keeps being blown away, buried, scattered, or removed before it builds up into a dark layer. The surface still changes, but the visible brightness does not record every speck of contamination in a simple way. Saturn's rings may work with a similar kind of hidden removal process. The rings are not passive. They are constantly being struck by tiny particles from space. They are being stirred by collisions. They are being shaped by moons. They are being exposed to sunlight, plasma, and Saturn's magnetic field. A grain of dark material that enters the rings may not stay neatly in place for billions of years. It can be shattered. It can be heated. It can be ionized, which means it gains or loses electrons and becomes electrically charged. Once it is charged, Saturn's magnetic environment can affect it. This means the ring's brightness may preserve less history than scientists once hoped. A clean ring surface may suggest youth, but it may also suggest efficient cleaning, constant recycling and loss. That does not erase the young ring possibility. Saturn's rings may still be only a few 100 million years old. The Cassini measurements of ring mass, brightness, dust, and falling material still make that a serious interpretation. But the newer twist means there is room for uncertainty. The rings may be young, they may be older, they may be a mixture of old material that has been refreshed, cleaned, broken apart, and rearranged over time. That uncertainty makes Saturn more interesting, because the ring system refuses to give one simple answer. It looks bright enough to suggest youth. It loses material fast enough to suggest a limited future. Yet the processes inside the rings may hide some of the evidence of their true age. So the story becomes less like reading a date carved into stone. It becomes more like reading footprints on ice while wind is still blowing across the surface. Some traces remain, some are erased, some are changed before anyone can measure them. And through all of this, one fact remains steady. Whatever their exact age, Saturn's rings are losing material now. Their past may be uncertain, but their present is active. The same processes that make them hard to date are also part of the reason they are slowly changing. So whether the rings are young, ancient, or somewhere in between, they are still temporary. The age debate changes the beginning of the story. It does not remove the ending. Saturn's rings may be young, perhaps only a few 100 million years old. They may be older than their clean brightness first suggested. They may have formed from a shattered moon, a broken comet, or a more complicated sequence of collisions and orbital changes that scientists are still trying to reconstruct. But whatever their origin, the rings are losing material now. Ring rain is happening now. Material is moving from the rings into Saturn's upper atmosphere. Cassini detected material falling inward during its final 2017 orbits. Infrared observations showed atmospheric patterns connected to magnetic pathways from the rings. Tiny grains can become charged, leave the ring plane, follow Saturn's magnetic field, and enter the planet. That present-day loss matters because it gives the rings a future. The rings have two clocks. One clock runs backward. It asks when the rings formed, what created them, how much material they began with, and whether they are truly young or only appear young, because the system can clean away some of the dark dust that strikes it. That clock is difficult to read. The evidence is mixed. Bright ice suggests youth. Ring mass suggests a limited history. Newer impact models suggest the rings may be better at removing dark contamination than scientists once believed. A shattered moon could explain the icy material, but the exact event remains hidden in Saturn's past. The second clock runs forward. It asks how long the rings can keep losing material before the broad, bright system we see today becomes thinner, darker, and less dramatic. That clock is easier to picture because the loss is already being measured. Material is falling. The rings are being drained. The system is active. A ring particle does not need to know how old the system is. A dust grain does not need to preserve the history of its formation. Once it becomes charged and follows a magnetic field line downward, its path leads away from the rings and into Saturn. That is why the future remains unsettling, even while the past stays uncertain. The rings can be mysterious in age and still temporary in future. A mountain can have an uncertain origin and still be eroding. A glacier can have a complicated history and still be melting. A coastline can have many ancient layers and still be losing sand grain by grain. Saturn's rings work on a larger, colder, stranger version of the same idea. Their origin story may be difficult to solve, but their present behavior still points toward change. This matters because the rings are often treated like a permanent symbol. They appear in textbooks, telescope images, classroom posters, spacecraft photographs, and children's drawings as if they are simply part of Saturn. But physically, they are a system with a supply of material, a rate of loss, and a limited future. They are not fixed scenery. They are an event, a long event, measured across millions of years, but still an event with a beginning, a middle, and an end. The beginning may have been violent. The middle is the rare, bright Saturn we see now. The ending may be quiet. No explosion, no sudden vanishing, only a gradual thinning of ice, a fading of brightness, a weakening of the wide bands, and a slow movement of material into the planet below. Future observers may inherit a Saturn that still has rings, but rings that look less impressive than ours. Farther in the future, the broad icy bands may be gone, leaving only faint dusty remnants, narrow arcs, or a much darker ring system. The exact timeline may shift as new research improves the models, but the direction of the story remains clear. Saturn's rings are changing. They are losing material, and once enough time passes, the planet that defined beauty in the outer solar system may look almost unrecognizable to anyone expecting the Saturn we know. The beginning is still debated. The ending is easier to imagine. Picture Saturn in the far future. The planet is still there. It still turns once every 10.5 hours. It still carries its pale bands of hydrogen and helium around its deep interior. It still has storms, lightning, auroras, a magnetic field, and a family of moons moving around it in long, quiet orbits. Titan still circles far from the planet, wrapped in orange haze. Enceladus may still shine as a small icy moon, though its activity could change with time. Mimas, Tethys, Dione, Rhea, Iapetus, and the smaller moons may still follow their paths through Saturn's system. But the broad, bright rings are gone, or nearly gone. The Saturn of that future would still be a giant world, but it would lose the shape that made it unmistakable to human eyes. The planet might begin to look more like Jupiter, Uranus, or Neptune. Enormous, distant, powerful, and beautiful, but missing the wide shining crown that made Saturn feel different from every other planet. There may still be rings. That is important. Saturn may not become completely bare. The solar system is full of dust, impacts, small moons, and debris. Faint material could remain around the planet for a very long time. Narrow, dusty rings may survive. Thin arcs may circle in the shadows. Small fragments may continue to orbit near the planet, shaped by moons and gravity. But the grand icy system we recognize could fade. The bright A ring, B ring, and C ring may thin out. The clean water ice may darken, scatter, or fall inward. The wide reflective bands that dominate telescope images may become dimmer and harder to see. From far away, Saturn might become a pale golden sphere with only faint traces around it. That image is difficult to accept because Saturn's rings feel like part of the planet's identity. But in the outer solar system, faint rings are common. Jupiter has a thin, dusty ring system, first discovered by Voyager 1 in 1979. It is made mostly of tiny particles knocked off small inner moons by impacts. It is so faint that it is almost invisible compared with Saturn's rings. Uranus has dark, narrow rings, discovered in 1977 when the planet passed in front of a star, and the starlight blinked several times before and after the planet itself crossed it. Those brief dips revealed rings that were too dark and narrow to see easily from Earth. Neptune has rings too, including partial arcs that look uneven and clumpy. Voyager 2 photographed them in 1989, showing that even the farthest giant planet carries debris around it. So a ringless-looking Saturn would still belong to the family of giant planets. It might still have rings the way Jupiter has rings. Faint, dusty, subtle, almost hidden. But it would no longer be the Saturn that fills posters, textbooks, telescope nights, and spacecraft images. It would no longer be the planet that children draw with a single tilted band around it. It would no longer have the same immediate silhouette. That is what the disappearance really means. The planet survives. The icon changes. Saturn, without its bright rings, would still be scientifically fascinating. It would still have one of the largest moon systems in the solar system. It would still have Titan, one of the most Earth-like worlds in chemistry and atmosphere. It would still have the North Polar Hexagon, deep atmospheric layers, powerful winds, and a magnetic environment shaped by rotation and charged particles. But emotionally, it would feel like a different world. A future civilization looking at Saturn might know from old records that the planet once had magnificent rings. They might reconstruct them from images, measurements, and ancient spacecraft data. They might study Cassini the way we study old maps of places that no longer look the same. They would know that Saturn once wore a bright, icy crown. But they would not see what we see. They would inherit the afterimage. And that makes the present moment feel rare. Right now, Saturn's rings are still wide, bright, and visible. Right now, they still catch sunlight and cast shadows on the planet. Right now, a small telescope in a backyard can still show the same basic wonder that confused Galileo more than 400 years ago. We are seeing Saturn during the chapter when its rings are still spectacular, and that chapter will not last forever. We are seeing Saturn during one of its most spectacular chapters. That is easy to forget because the rings have been present for every generation that ever studied the planet through a telescope. Galileo saw their strange side shapes in 1610. Huygens recognized the ring in 1655. Cassini saw the dark division in the 1670s. Voyager flew past in 1980 and 1981. Cassini orbited from 2004 to 2017. Every one of those human encounters happened during the same bright ring era. So to us, this is simply what Saturn is. But on the planet's real clock, this may be a brief interval. Saturn is about 4.5 billion years old. Human telescope history covers just over 400 years. That means our direct visual record of Saturn covers less than 1/10,000,000th of the planet's lifetime. We have watched only the thinnest sliver of its story and happen to arrive when the rings are broad, reflective, and dramatic. That makes our view strangely lucky. A few 100 million years earlier, if the young ring interpretation is right, Saturn may have looked far less familiar. It may have been a giant planet with moons, storms, auroras, and faint debris, but without the wide icy bands that dominate its image today. A few 100 million years from now, the broad rings may be dimmer, thinner, or largely gone. The planet would still exist. The moons would still move. The sun would still shine weakly across the outer solar system. But the Saturn that fills our imagination could belong to the past. Future observers may study old spacecraft images the way we study fossils, ancient shorelines, or dried riverbeds on Mars. They may look at Cassini photographs and see a lost version of the solar system. A version where Saturn wore bright rings across hundreds of thousands of kilometers, where those rings cast shadows onto the clouds below, where the planet looked almost impossible. And they may understand that their Saturn is later in the story. This is what the rings reveal. Even giant planets have chapters. They form. They gather moons. They lose heat. They absorb impacts. They move through changing space weather. Their moons migrate, crack, warm, freeze, erupt, and sometimes break apart. Their rings appear, spread, darken, and fall. The solar system often feels finished because its largest structures change slowly. The planets follow stable paths. The same worlds return to the same parts of the sky. Jupiter remains striped. Mars remains red. Saturn remains ringed. But stability can hide motion. The Moon is drifting away from Earth by about 3.8 centimeters each year. Mars has dust storms that can cover the entire planet. Jupiter storms merge, shrink, brighten, and fade. Enceladus sprays water vapor and ice from fractures near its south pole. Comets lose material each time they pass close to the Sun. And Saturn's rings are falling into the planet they circle. The solar system is still active. It is still being shaped by gravity, impacts, radiation, tides, magnetism, and time. The drama has slowed since the violent early days, when planets were forming and large bodies collided more often. But it has never fully stopped. Saturn's rings make that truth visible. They are a beautiful structure, but they are also a time marker. They show that even after billions of years, a planet can still change in ways that alter its identity. A moon can become debris. Debris can become a ring. A ring can become rain. Rain can become part of a giant planet's atmosphere. This is why the present view of Saturn matters. We are seeing the planet during a rare overlap between human existence and ring brightness. A small technological species on a small rocky planet learned to grind lenses, build telescopes, launch spacecraft, and photograph Saturn at exactly the right time to see its rings in their full splendor. That does make the rings feel more fragile. It also makes them feel more valuable. They are temporary, and we are here while they are still visible. The story began with a planet that seemed permanent. It moved through invisible rain, broken moons, spacecraft measurements, and uncertain ages. Now it opens wider. into something larger than Saturn itself. The rings are disappearing because the solar system is still becoming something else. Saturn's rings now look different than they did at the beginning of this journey. At first, they seemed like a permanent crown around a distant planet. A bright, balanced structure that had always been there, simply waiting for humans to invent telescopes and notice it. But the rings are far more fragile than they appear. They are thin. In many places, only about 30 feet thick, or roughly 10 meters, even though they stretch across hundreds of thousands of kilometers around Saturn. From far away, they look like solid bands of light. Up close, they are a moving swarm of countless icy fragments. Some pieces are smaller than dust grains. Some are like pebbles, snowballs, boulders, cars, or houses. Each piece is orbiting Saturn separately, falling around the planet at thousands of meters per second, held in place by gravity and motion. The rings survive because of balance. Saturn's gravity pulls inward. Orbital speed carries the particles sideways. Collisions flatten the material into a thin plane. Nearby, moons carve gaps, raise waves, sharpen edges, and keep parts of the system organized. But that same system also creates loss. Tiny grains can become electrically charged. Once charged, they can interact with Saturn's magnetic field. Instead of staying neatly in the ring plane, some are guided along magnetic field lines into the planet's upper atmosphere. That is ring rain. It is a strange, invisible flow of icy material from the rings into Saturn itself. It does not fall like rain on Earth, landing on soil or collecting in rivers. Saturn is a gas giant, made mostly of hydrogen and helium. Ring material enters its upper atmosphere, changes the chemistry there, and becomes part of the planet. Cassini helped reveal how active this system really is. The spacecraft arrived at Saturn in 2004 and orbited until 2017. It watched the planet, rings and moons for more than 13 years. During its grand finale, Cassini flew between Saturn and the inner edge of the rings 22 times, measuring gravity, dust, charged particles, and material falling inward. Those final measurements helped turn the rings from a beautiful image into a physical system with mass, motion, chemistry, and a future. They also deepened the age mystery. The rings are bright and icy, which has often suggested youth. Clean ice should darken over time as micrometeoroids strike it and add darker material. That helps support estimates that Saturn's bright main rings may be only around 100 million to 400 million years old. That would make them extremely young compared with Saturn itself, which formed about 4.5 billion years ago. But newer ideas complicate that clock. Micrometeoroid impacts may vaporize material and create charged particles that are pulled into Saturn or ejected into space. If the rings can remove some of the dark pollution that hits them, then they may stay cleaner for longer than expected. So the rings may be young. They may be older than they look. They may be a system that refreshes, loses, and hides parts of its own history. But their future remains temporary. Ring rain continues. Material keeps leaving the rings and entering Saturn. The exact timeline may shift as scientists refine their models, but the direction is clear. On the scale of planetary time, Saturn's rings are a passing structure. Maybe they formed from a shattered icy moon, Maybe a comet or smaller body came too close. Maybe Saturn's Roche limit, the invisible region where tidal forces can pull a body apart, helped turn one broken object into billions of orbiting pieces. Whatever began the rings, time is now changing them. A moon may have become debris. Debris became a ring became rain. And one day, far in the future, Saturn may look less like the planet we know and more like the other giant worlds. Still immense, still powerful, still surrounded by moons and faint traces of dust, but missing the broad, bright crown that made it famous. That is what Saturn's rings teach us. The solar system is still moving, still changing, still writing and erasing its own chapters. We are seeing Saturn during a rare moment, when its rings are still wide, bright, and visible. A small window in the life of an ancient planet. A time when ice still circles the world in shining bands before slowly falling into the clouds below. So the next time you see Saturn, picture more than a distant planet with rings. Picture a giant world wearing the remains of something broken. Picture a crown made of ice, dust, gravity, and time. And picture that crown slowly falling as rain.